So last week, well, it was last week, since that you guys had a week of break, we started discussing about affine and projective transform of images. What is an affine transform? An affine transform is something that allows a straight line to remain straight lines and parallel lines to actually remain parallel. However, for some transformation, rectangles may become parallelogram. So transformation included under the category of, under the umbrella of an affine transform are scaling, stretching, shearing, and so forth. Because some of them, they are performed all the time, they have dedicated functions inside MATLAB to perform them. Otherwise, if the transformation you want to operate on the image is not included, well, is not supported as a function or script on its own, or you want to make your own shearing or stretching that is customized because you're doing some specific job, then MATLAB allows you to do that using the routine make_t4, which basically means make your own transformation. So obviously there are some of them where you can use actually points or landmarks to generate some specific transformation, like rotation around the point, shearing around the point, or transform everything but not this point, basically. So there are a way of doing all these kind of things, and they are included into that. So the most common way of doing it is using im transform. And if you just type help im transform into MATLAB, MATLAB will explain you how im transform works and explains you all the parameters that you need to give to im transform to operate, like the input and the output image, and the parameters and the value of the parameters that you want to operate. So particularly you can allow or not allow the pixel to change in size, because remember that when you do some operation like rotation or stretching, the image changes size. Now what do you want to do? Do you want to change the size of the pixel according to the transformation, or you want to increase the size of the image, limiting the size of the pixel? So all these kind of things, they are supported by im transform. So I have a couple of examples, but in general, this particular function make_t4 can actually be used to specify an affine or projective transformation. In general, only 3 points are required to define an affine transformation. You need different number of points for a projective transformation. So this is an example of shearing, and we're going to see it in a second with the code. So you basically specify the input triangle, and you basically decide what is the shifting of those points, and you obtain a shearing of the image.
What's the shearing process to? I didn't get what.
It's like, well, it's a well-defined kind of rotation, if you like. It's a deformed rotation, put this way. So what you do, you just define a direction, like in this case, And you don't just rotate the pixel, but you compress the pixel according to the amplitude of the shearing. Okay? So put this way, that basically how much you shift this is going to be the main axis of rotation. How wide is this triangle is how much you want to deform the pixel to fit into that image. Okay? Projective transform, they do a different things than affine transform because they are used to actually add the perspective points or remove perspective points for your image. So say that it means that parallel lines, they might not remain parallel after the transformation, and actually is most likely the case that parallel lines, they will have a convergence or a divergence. Okay? So in order to define this transformation, you need to define 4 points, because you need to define where the convergence of the parallel lines goes. The idea is based on the perspective feeling that we have when we look at some very large landscape that seems that all the parallel lines, they seems that they converge towards infinity. So using 4 points instead of 3 allows you to basically decide when parallel they need to meet. With this kind of transformation, you always define where the parallel they go, where they close down. With a projective transformation, you don't, or you actually say when this happen, defining this other dimension, so 4 points. You can reduce a projective transformation to an affine transformation if this distance is 0. But if this distance or this other distance is 0, then you are specifying 3 points and not 4. Make sense? This is quite enlightening, that allows you to understand the difference between the two kinds of transformation. So this is the original file. This is our affine transformation that we just specified, that we give the 3 points and we do the shearing, so that is a tilting and compressing of this slice to fit into that specific pixel area. Instead, those are 2 different kind of projective transform of the same image. If you think about it, and if you just look at 1 and 2, and then 2 and 3 over here, you understand that it's basically like taking the image, tilting it forward or back. It's like that you take anything, something flat, yeah, the power supply, and you do like this, but without changing your observation point. Obviously, what you see is different, when it's projected on your observation point. All right? So that is why this function, this transformation, are called projective. Because what you do, you change the projection of your object onto the plane of sight. Okay? So this is probably with a 2D image, this doesn't make too much sense. However, if you have a bunch of slices of a brain scanner and you do this operation with all of them and you stack them together to form the 3D image of the brain, then you can rotate these things in any arbitrary position. Of course, there will be voids that they have to be filled by the processing, because you are not able to rotate these things where you don't have data unless you do interpolation and things that we've seen. But you understand now where this thing goes. You do on a 2D image, you do it on every slice, and then you compose them together. So when you have the 3D reconstruction, 3D of the head of a patient out of a 3D MRI or CT scanner, when the doctor simply rotates, well, all those transformation and sometimes combination of affine and projective transformation are required to make the image to move. They are computed in the background and the results stuck together and presented. And now you can understand why sometimes, if you play too much with these things, and I have seen it, then the system goes crazy because it does not have the time to compute properly, and you just already are queuing another rotation, and then the image gets very crazy, and the doctor has to reset the display.
Like he can have all the transformation in one picture, it has to be separate.
Yeah. Well, it depends on what you're interested. If you just want to rotate, say, the mesh of the face reconstructed from the slice, or the mesh of a particular part of the surface of the brain also reconstructed from the different stacked slices, then you only have to process those. But if you have the entire things, every transformation, every slice needs to be processed, and then the image needs to be reconstructed. Okay? So I have some example about these things that I want to quickly go through with you, and then I would like to spend a bit of time on the Lab 1 solution, because I'm a bit disappointed. Only 2, they've done a good job out of 7 submissions.
Yeah, we all done some mistake. We used low pass filter, which is already we know that.
We'll discuss this thing. So these are some examples that you also can find on the book. Particularly this one was introduced the past lecture. And this is the typical affine transform of rotation. So this is the original image, which is a scan of a tissue, physiological tissue. And we just want to rotate it of an angle that we decide. I think this one was 30-degree clockwise or something, whatever it is. When you rotate it, because you need to preserve with this particular transformation the angles, so parallel lines remain parallel, and rectangle or square, they remain rectangles or square. You need to do interpolation to reconstruct the boundaries of the new image. And you're going to end up with an image that is way larger than the original image. Obviously, if you do a full 90-degree rotation, well, that is, although it doesn't seem intuitive, it is still a transformation, But the size of the image into the memory doesn't change, because you just basically transformed the horizontal frequency into the vertical frequency and vice versa, but you haven't changed the size of the image, because if the image is a square in particular, well, you can rotate it of 90 degrees at a time every time you like. The size of the image never change. But if you do something that is less than 90 degrees or more than 90 degrees, but not 180 of course, then you're gonna have this problem. And this is the reason why you have those black boundaries. And you have to tell to MATLAB and to any other image processing software how to do the padding of those added pixels. You can pad them with zeros, or you can pad them with the maximum luminance, which is going to be white in case, well, is always white, but you could choose, in case of an RGB image, any specific background color you like for those added pixels. Okay, normally our choice goes to the zero padding, which means black for the added pixel. You might have constraints into memory, or you might not be interested into the added pixel, and you can afford to lose actual information, cropping the image back to the original size. So these two images, they have exactly the same size. However, they don't have the same informative content. So these two images over here, they don't have the same size, but they preserve the informative content. Same size, but loss of information. Sometimes you have to do one of the two. This is the case often that you do all this kind of rotation and cropping, where when you have full slices of a body where the entire body width wasn't fitting into the size of the scanner. So that's typically the case when you have a sample, you have a very small CT scanner. They're called a tabletop CT scanner. Believe it or not, they are very small. By the way, a CT scanner that you probably have seen in operation many times is the CT scanner into the airport. The one where all the luggage goes through. So anyway, when the scanner size is a constraint, but you need to basically reproduce the full inner image of the object, which could be a sample like a large piece of concrete or something, then what is done, the sample is chopped in two halves. You do the scanning of the first part, the scanning of the second part, and then of course you might need to rotate them to reattach them together. And probably you do the images of the piece that needs to be rotated from several angles. And then you reconstruct all the missing parts with this transformation, and you're gonna end up with a stitching. Sometimes this is done more trivially when you do the panorama stitch. If you want to take a picture of something that is too big for your lens, what do you do? You take a picture of a part with an overlapping bit, then you move across and you stitch them together. One very famous panorama stitch is the wreck of the Titanic, that the unmanned submarine robot forgot how many hundreds of meters that thing sits in the water. He went and started from the bottom, took pictures of this thing, and then the computer realigned them with lots and lots of black boundaries where the machine couldn't take the picture. So Google for those things. You'll find them very interesting. Anyway, so this is an idea. This is one example, and I put it up here, and we discussed it last lecture. Although this seems very silly, because you lose information, sometimes has to be done. Using the same image, we can do a comparison between affine and projective. So this is exactly the same kind of shearing that we've seen for the MRI frame from the book, where you actually define the 3 points and you squeeze and rotate the image. Or you can decide to take your tissue sample, project it, like seeing from different angles. And these are just some value I was playing with when I made this example, but you can actually take this image or the MRI image from the book and play with it. Because actually it's pretty interesting. Particularly when you go on very acute observation angle that you actually change the image quite a lot. And that's what I have in terms of lecture. So we have a good half hour to discuss